So can you all hear me? Go louder? Okay, good. So thank you so much for having me today. It's always a pleasure to come back to Caltech. So today I'm going to talk to you about this new adventure in multi-messenger astrophysics that's now using gravitational waves. I'm going to be talking about the work that we've been doing with the LIGO and Virgo collaboration. I'm going to be talking about the discoveries that have been done, which you have probably already heard about, but so I'm going to try and summarize what we have learned from them, tell you about what's happening right now, and some new directions for the future. So what's the outlook for the next decade or two? So I will start with a very brief introduction of gravitational waves. Gravitational waves are perturbations in the fabric of space-time. They were predicted by Einstein as part of the theory of general relativity, and they are produced by rapid changing in the shape and orientation of massive objects. As such, they carry information about the coherent relativistic motion of large masses, which is a different type of information from what we learned from the electromagnetic radiation that's coming from oscillating charges. They propagate at the speed of light. They are transverse waves, and they have two polarization, the so-called plus and cross polarization. So here you see the path of a gravitational wave and the effect that they have on matter. Remembering that GR is about geometry, so it's a stretching and squeezing of space-time transversally on the path of the wave. Realistically, effectively, physically, what we see is a dimensionless strain, which we call h of t, which, if we are at the receiving end, is inversely proportional to the distance from the source, and it depends on the second derivative, so the acceleration of the source mass quadrupole moment. So to produce gravitational waves, we need acceleration of asymmetric objects with a quadrupole moment. And so the best understood source of gravitational wave is what comes from the in-spiral merger of two compact objects, such as black holes or neutron stars, which you see depicted in this cartoon. And so assume these are two black holes or two neutron stars. They in-spiral around each other. As they do so, they produce the formation of space-time that propagates as a wave, and we're going to be receiving this billions of years away from the production point. So how do we go about detecting gravitational waves? Well, if we can imagine a ring of suspended test masses and the gravitational wave going into the plane of the board here, this is the effect of a gravitational wave in the plus and in the cross polarization. So a circle is stretched and squeezed into an oval in the 90-degree and the 45-degree directions. If we now assume that at the center of this circle, that's to be two arms of an interferometer, then a way to go after these small changes in the metrical space-time is to go after changes in the relative length of the two arms. And this happens with the frequency of the gravitational wave itself. And so that's the fundamental principle behind LIGO, which you see in this aerial picture over here. This is one of the two detectors. The idea is to measure relative changes in the length of the two arms by using interferometry. So we have a laser beam split around the two arms, recombine, and we look at the output port. So this is a very schematic, cartoonish, if we want, design of the initial LIGO detector. Here are our suspended masses, the 2n masses. This is the beam splitter. This is our laser beam. The light travel on the two arms, recombine. And as the gravitational wave comes through, it changes the relative length of these two arms. The two arms are 4 kilometers long. And the effect that we're going after is actually rather small. The strain that we are pursuing, such as what's produced by a binaneutron star in the Virgo cluster, for instance, is of the order of 10 to the minus 22. So what we really are going after are changes in the length of these arms, which are of the order of 10 to the minus 19 meters. And so that's part of why it has been so difficult to, such a long process to get to this discovery, is that this is very precise measurements where we are fighting with the quantum limits. So LIGO stands for the Laser Interferometer Gravitational Wave Observatory, as you probably all know, being here in Caltech. So the observatory has two sites. One is in Hanford, Washington. The other is Livingston, Louisiana. The laboratory is jointly operated by Caltech and MIT and is funded by the National Science Foundation. This is a project that started in the 90s. So construction of initial LIGO was between 94 and 2000. We acquired data between 2002 and 2010 in the initial LIGO configuration, which is very similar to the design you saw in the previous sketch. And then between 2010 and 2015, there was an upgrade campaign to Advanced LIGO. So Advanced LIGO has so far had 3 data acquisition run, 01 in 2015 to 2016, 02 in 2016-2017, and we are now in the 3rd science acquisition run. We're about halfway through it. And we're going to tell you about the results that have been obtained in 01 and 02, and then tell you where we're standing with 03. This is it's another, if you want, conceptual sketch of now Advanced LIGO. So going from initial LIGO to Advanced LIGO, what's changed is that, well, the real estate was maintained, but pretty much all the parts of the components have been replaced and upgraded. So the laser beam was upgraded to a more powerful laser that could potentially reach 150 watts. The suspensions have been modified. So while in initial LIGO we had basically a simple pendulum, so the smaller mirror hanging on a guitar string, we now have a system, a complex system of a quadruple pendulum that is supporting a 40-kilogram high-quality fused silica mirrors. And this has been designed to better defend the detector from one of the biggest noise sources, which is the seismic noise. There are more than 300 control loops needed to keep the interferometer optimally running. These are Fabry-Perot cavities, so the laser beam bounces back and forth at the point that we have order of 100 kilowatt power within the cavity. And then as the two recombine, powers an additional cavity over here to amplify the outputs. And then what we look at is a time series, which is read at the output port over here. So if we take that and make it into a power spectrum, this is how we normally look at our sensitivity. In this kind of plots, where here we have the frequency of the gravitational wave going from 10 Hertz to 10,000 kilohertz, 10,000 Hertz. And along this axis, there is this quantity, which is a strain in units of 1 per square root of Hertz. That's the square root of the power spectral density. And so this is the typical shape of the LIGO noise sensitivity. And what is depicted here are the major limiting noise sources. So it's kind of hard for me to strain my neck over here. But on the high frequency, the limit for Advanced LIGO is quantum noise. So it's basically shot noise due to the fact that we're looking at very few photons coming out from the dark port over here. At medium intermediate frequency, the limiting factor is the Brownian motion in the Brownian noise on the coatings of the mirror. And then at lower frequency, we continue to remain limited mostly by suspension and thermal noise. So thermal noise in the suspensions combined with the seismic activity, seismic noise wall over here. So those are the 3 limiting factors that remains for the sensitivity of Advanced LIGO. This is a global quest. LIGO is not the only experiment that's pursuing gravitational waves. We have, well, first of all, there is GW600, which is a 600-meter baseline interferometer in Germany. It's part of the collaboration, and it's mostly used now in astrowatch modes or for R&D for advanced technology, in particular the squeezing developments. Virgo is a detector that's a sensitivity now comparable to the one of LIGO, and I will say more about that later. It's in Italy. It's a 3-kilometer baseline detector. And with Virgo, we've been, for a long time now, exchanging data and working together. So we really talk about ourselves as a LIGO-Virgo collaboration. And then there is Kagra in Japan. Kagra is trying to do something even more challenging. So what they're trying to do is to operate an interferometer underground with the goal of operating it cryogenically. So going underground is a way to address seismic noise issues, because the seismic activity is actually lower underground than above ground. And then operating cryogenically is a way to address the thermal noise limitations. Now, they are planning, hoping to join our next run, our ongoing run, by the end of the year. And we have now joined an agreement so that we are going to be talking about the LIGO-Virgo-Kagra collaboration from this point on. This is an outlook of how big the collaboration is. We have grown over the years, 1,400 members, 100 institutions, 18 countries. So it really is a widespread effort, and many of you are in this room right now. Okay, so now I want to talk a little bit about the science that LIGO can do. So when we talk about gravitational wave astrophysics, there are 4 basic classes of sources that we pursue. So there are the coalescing binary system. That's the system that I talked about earlier, 2 compact objects that inspire and merge. So that's the best understood, the best model system, and that's where we've had discoveries so far. So I'm going to be saying much more about that in the next few slides. We have another class of transient sources. We refer to them as bursts. So these are all those other short duration or transient gravitational wave sources for which we don't have a very well-defined model, for which we don't have a waveforms that we can reliably use in a much filter type of search. So this is a broad category. It includes core collapse supernovae, cosmic strings, soft gamma ray repeaters, pulsar glitches, and any of those. This is where we put the unknown, so things that may be out there, but we don't know what they are yet. So this is our surprise category. These are both transient type of sources. Then when we go and look at long duration type of sources, then we can start talking about continuous waves. So continuous sources are, for instance, production of gravitational wave due to pulsars that rotate around their own axis, and possible bumps or mountains on the surface of a neutron star would produce enough of that accelerating quadrupole moment to produce a gravitational wave that's pretty much constant in frequency, modulo Doppler effect. And then we have a stochastic gravitational wave background. So this is that stochastic background noise, which could come from 2 types of origins. Cosmological backgrounds, that's the residual background from the Big Bang. That's where, if we find it, we can find out what happens in those 10 to the minus 40-something seconds after the Big Bang itself. And the other is astrophysical stochastic background. So this is basically the overlay of all of those binary mergers that have happened, all those supernovas that have happened and have left an echo in the universe. And so it's kind of more recent in age. It's coming from the era of stars, but it's out there, and we treat it as stochastic because it's not individualized sources. So these are the 2 types of stochastic backgrounds that can be pursued. And so these 4 categories are being analyzed and looked for separately, but so far discovery has happened only in this box, and so that's what I'm talking about now. So there have been 2 groundbreaking detections, discovery that I'm sure you've heard a lot about by now. One is GW150914. That's the first discovery of gravitational wave background from the collision of 2 black holes. That took place just about 4 years ago. And then there is GW170817. So that's the first, and so far the only binary neutron star merger that we have that we have positively identified and follow up. And this took place 2 years ago now. And each of them has been marking a breakthrough moment, because in this case, we had our first discovery and evidence of the existence of gravitational wave. In this case, we had, for the first time, an event coming from a collision where matter was involved, electromagnetic radiation was produced, and so this was the first multi-messenger discovery included or triggered by gravitational waves. So I'm going to say something about what we learned about black holes and then neutron stars as well. So starting from black holes, this is the first discovery. It's the first signal that was seen in Hanford and in Livingston. This is data that was just simply bypassed, so no special filtering took place. Over here, you see the numerical relativity waveform that matches this signal in the data, the residual, and the typical chirp feature of a binary black hole merger. So this is a signal that increases in frequency and in amplitude over time as the two objects rotate faster and faster around each other until the point where they collide and merge. What you see over here is what general relativity would tell us about this signal. So this is a typical in-spiral, merger, and ring-down of a merger of two black holes. And down here, we see from GR, we can predict as the two get closer, as the two objects get closer and merge, what was the distance between the two black holes and what was the relative velocity of the two black holes. So according to general relativity, these two black holes had a Schwarzschild radius of about 200 kilometers, and they merged when they were at about 3 Schwarzschild radii distance from each other. So just to give you a sense, a black hole center on LA and one center on Phoenix, their masses were about 30, 40 solar masses each, and they were rotating around each other at a speed of 0.6, this time the speed of light. So this was a very energetic event, which ejected about 3 solar masses worth in gravitational waves, and that's a signal that we received 1.3 billion years later. So that was the first. We have had more. So from the first science run, we had 3 pairs, 3 binary black hole collision identified. And so for those of you who are not so familiar with this waveform, just a couple of words on what this waveform look like and why are they different. So the frequency at which the merger happens depends on how fast the two objects are rotating right at the time they come in contact. And that depends on how big the objects are. So roughly speaking, the frequency of the merger is inversely proportional to the total mass of the black holes that are involved. So if we compare the waveforms to the LIGO spectra, so these were the Hanford and Livingston spectra at the time of 01. These were the 3 events that were identified. One had 65 solar masses total, 37, 14. And so the frequency for merger was lower for this one, intermediate, and then went all the way up to close to a kilohertz for this last event. And so this is how is determining basically how many cycles in our bands are detectable. So the length, the time duration for the signal that we see. The amplitude of the signal is instead correlated to how far the source is, that 1/r factor that I was showing in the second slide. And so this was the first event. It was the loudest and the most massive of the 3. And so it's a short waveform, and it's also louder in amplitudes, so higher H. This was a very weak one, very low signal-to-noise ratio. It was very far away. And this one is the one for which we had the most cycle, lower solar mass, and then how it relates to the other two. So that's pretty much to give you an idea of how, just with the first look, we can look at the signal and know the mass of the objects involved and the distance as well. In the search, we then compare to what's the probability that this thing happens by accident. So these were those three events compared to the background. So we have a detection statistic, which is the network signal-to-noise ratio. This was our loudest event compared to what we get by shifting or delaying the time series in the two detectors. That's our background estimates. And so this was our first. Once we removed that, we had our second event. And this event here in green, there was something that initially we didn't even know for sure was a detection. Well, for that one, the false alarm probability was actually higher, which means we had a lower significance assigned to this event. Anyway, this is the kind of analysis that's been done to extract the signal from the data and declare their detection. We have had more of this. About a year ago, we published this first catalog of gravitational wave transients from the LIGO Virgo data. So combining the first and the second data run, we have now a set of 10 binary black hole events and the binary neutron star. So each of these has some differences in how long is the waveform, how bright or how loud the signal is, and that has to do with the relative distance or the relative masses of these objects. In some cases, it's probably hard to see, but there are different effects of modulation, so that goes for the spin, and I'm going to say something more about that next. This is the binary neutron star signal. So while all of these signals were a fraction of a second, just a few cycles in band, the binary neutron star merger, because those were much smaller objects, the frequency of merger is much bigger, and so we had many more cycles in band. So the signal for the binary neutron star was closer to a minute, okay, so much longer in duration. And that allows a much more accurate characterization of the waveform. In terms of the masses, we are now starting to populate a map of black holes, basically, that have been discovered through gravitational waves. Before the discovery, there was no guarantee that these heavy solar mass black holes, so black holes with masses of 10, 30, 40, 50 solar masses, even existed. This is now the most robust evidence that these black holes actually are out there. There are questions about how is it possible to have such a big black hole. So that led to the conclusion they're most likely formed in a low metallicity environment. And that's because lower metallicity means fewer stellar winds. And so the star retains more of its mass before it collapses to a black hole. The merger rate is between 10 and 100 per cubic meter per year. And then if we look at the distribution of the masses for all these black holes, well, their Bayesian inferring analysis is disfavoring the existence of black holes with mass larger than 50 solar masses before the merger. After the merger, of course, they're bigger. Now, this is consistent with limits coming from supernova modeling due to pulsational pair instability supernovas. So the fact that pair production in the bigger stars takes mass away, and so it's hard for the star to retain enough mass to get into a black hole larger than 50 solar masses. So this is, with the 10 pairs, so we have 30 black holes that are being considered now in this distribution, and that's destined to grow as new data is coming in. The other thing we can look at is the distribution of masses. Again, we only have a statistic of 10, so it's early to make distributions. But we have now 6 sources that are farther away than 1 gigaparsec. The most distant source is at 3 gigaparsec. The closest one is 0.3 gigaparsec. So the distances are all at the order of the gigaparsec level, to be compared to the BNS, which was at 0.04 gigaparsec, so 130 million light years. So that's a much closer source. And so we can see that far because in a binary black hole, more energy in gravitational wave is produced. The other thing we can look at is the spin. So when we look at the black hole spin, there is a fundamental degeneracy that we need to consider. So what we are mostly sensitive to is this quantity called chi-f, which is basically the projection of the total spin on the angular momentum for the system. And so we are not able to discriminate the planar component of the spin. There is degeneracy there. So this is for those 10, those 10 sources, the distribution, the posterior distribution for the chi-effective. And what we see here is for one particular event, GW150914, which is, let's see, it's this one over here. This one. We see basically what's the posterior probability distribution for the actual spin and their orientation. And now there are large errors on these numbers. What we can say is that for at least that one event, the distribution of chi-f is, they're all consistent with 0 but slightly negative. And looking at the individual distribution, there is some possible indication of non-alignment of the spins. Okay, so that's all we can say from this. It's not a very strong statement. But why is this important? Because once we get more of this, once we actually have distribution of spins, that is actually something that can inform formation models. So did this black hole pair form as an isolated binary evolution or dynamical formation in dense clusters? Were these two stars that were already in a binary system, one goes black hole, mass accretion, exchange of angular momentum, thus alignment of the spins, or is this something that comes from two black holes that form independently and then found each other, each with their own spin? And so this kind of evidence, the spin actually is gonna give some clue into formation models. Another degeneration that we have is with the plane, the orientation of the plane. So what you see here is a simulation, is a numerical simulation of two spinning black holes that are rotating around each other. And as they do, the plane of rotation is kind of wobbling. So the colored area there is the north pole for the black hole itself. And so now you see it slow down, and you see there are this kind of deformation, this wobbling, and the reorientation of the plane of the orbit. The second, let me replay this while I'm talking. The second set of pictures down here, these are the two polarization, the plus and the cross polarization, which are fundamentally different. So once we start having spinning systems and the wobbling plane, it becomes important to disentangle the polarization to be able to say something more about the precessing nature of the system. Now, with two detectors, we are not able to deconvolve the polarization of the system. This is one of the reasons why we need to have a network with more detectors. Other things that we can learn, while it would be good to have the ringdown, we haven't been able so far to identify the ringdown. So that's what happened after the two black holes merge, and we have an excited system that wobbles and then decays. Seeing the ringdown is going to be important to do tests of general relativity, check the no-hair theorem for black holes. And so there is a lot of potential into detecting the quasi-normal modes in this ringdown. We haven't done that yet. However, there is already a place for numerical relativity to come in and teach us ways to extract information in a model-independent way. So this is just as an example of exploratory work that's been done now on measuring what's the final spin from the data at merger, just by looking at the instantaneous frequency at the time of the merger itself. So I'm not going to have time to go through all of the details of this, but this is just to say that there is something we can learn even without having accurate match filtering and a broad bank of numerical relativity waveforms. We can extract kind of phenomenological relationship between the frequency and merger and the spin, for instance, that can give us information on these black holes, even though we don't have the exact numerical relativity simulation for it. And this is important when it comes down to precession, which is a complex problem. The other thing that we can learn about these black holes is the sky localization. So most of these black holes were identified only by the LIGO Livingston and Danford pair. Once Virgo got to be online and we had 3 detectors, that really increased the ability to localize the source, not on a ring, but in a region that could potentially be followed up by telescopes. So these sources that you see here circled here, those were the 3 events that were simultaneously detected by LIGO and Virgo. And so, for instance, this is the binary neutron star that I'm not told you much about yet. These were 2 black holes mergers, so 170814 and 170816. 18, sorry. So those were all taking place in that 1 month when LIGO and Virgo were operating at the same time, August 2017. So, and this is what really gave the potential for follow-up, which is so important to enable multi-messenger astronomy. So the idea here now being that when we have 2 neutron stars that merge and produce gravitational waves, besides gravitational wave, we're also going to have electromagnetic radiation across the full spectrum, and possibly high-energy neutrinos. Neutrinos could be produced as well. So the next excitement is now coming from joint detection across all of this type of experiment coming from the same source. And the first time that this was possible is when GW150914 was discovered. So GW150914 is a binary neutron star merger. So you see here the last few seconds of the signal as it appeared in the gravitational wave data. And that was discovered within 1.7 seconds of a trigger from the Fermi satellites. So this was a very important first coincidence that we now know is associating the binary neutron star merger as a source or an engine for short GRBs. And it triggered a multi-messenger campaign that made this into the most observed astrophysical event so far. So this is a very complex plot that I'm sure many of you are actually co-authors on this paper itself. It's just pretty much to show the plethora of measurements that took place. This event was observed in optical, UV, infrared, radio, X-ray, gamma, and gravitational wave as well. So it's the first time all of these sources were brought together. And I'm going to accelerate this a little bit. I don't think I need to talk about this. I'll just go straight to this. And the reason why the follow-up was possible is that not only the 2 LIGO detectors were operating, but also Virgo was operating at the time. And Virgo actually did not see the event itself, but it turns out that's because the event was in the blind spots for Virgo. So the fact that Virgo was taking data and did not see the signal allowed to reduce the error region for this event to an area of 30 square degrees. And so that made possible the follow-up campaign. The event was identified by 6 telescopes within a period of, I believe it was 12 hours. And so we had, for the first time, an actual image of the event. So it is in a swap image, and this is the location the day before. So the event was not there the day before. So this has enabled a rich plethora of science that I'm not going to be expanding on. So correlation between binary neutron star merger and gamma ray burst. It has enabled a new way of measuring the Hubble constant and doing cosmology by using binary neutron stars as standard candles or standard sirens to measure the scale of the expanding universe. And the identification of a kilonova following the events allowed us to to correlate the baryon-neutron star merger with formation of heavy elements. So that's lots of rich science that has happened since. On our end, we have learned how to infer neutron star properties by doing a parameter estimation campaign to extract things like joint distribution for M1 versus M2, so the mass of the two neutron stars, measuring the spin versus the Q, which is the ratio of M1 versus M2, and then go after neutron star structure itself. So for the first time, we could actually go after tidal deformation, look for evidence of tidal deformations, which is connected to the equation of state of the neutron star, and start to put limits on possible equation of state models, which now seem to favor, in our data, more compact objects. So these are very early stages in using gravitational waves to measure the equation of state of neutron star, but it's a strong potential that is going to increase as more data is acquired. Okay, I think I'm going to have to skip some of this. But now, looking at things to do in the future, one of the big area of interest is now bringing together gravitational wave and astrophysics and nuclear physics, looking all together at the equation of state of the neutron stars. So why is that important? Because what we can learn from the neutron star is actually can be matched by measurements in nuclear physics. It's the connection between the microscopic and the microscopic, micro and macroscopic, and ways in which we can look for evidences of the effect of the equation of state in the gravitational wave data by itself are, for instance, looking in. So these are curves for initial LIGO, advanced LIGO, and Einstein telescope. So that's the third generation of detectors. This is what a baryon-neutron star merger looks like before its merger. And now the details of what happens right before the merger and the existence of a post-merger peak is depending on the equation of state itself. So these are two different models that are connected to what is the destiny of the neutron star merger itself. So whether the merger takes us to a prompt collapse or an hypermassive remnant, which decays within less than a second, or a supramassive remnant, which lives for a few more seconds, or it's a stable remnant, that's going to manifest itself into the existence of a post-merger peak in the gravitational wave signal at high frequency. And so pursuing that is a way to and all of this depends on the equation of state itself. So how compact it is, how squishable it is, it's going to affect the size of the star, and not only the size, but also the extent of tidal effects right before the merger, and the frequency of this post-merger peak, and the delay between the merger and the post-merger itself. So this is an area of great excitement looking at the future. We have not seen evidence of post-merger peaks yet, but the hope is that with future experiments, this will become indeed possible. So what's the current status? So this is a layout of the current plans. So we are now in this third science run. The runs here are characterized, are qualified. The metric we have is the range for baryon-neutron stars, so how far can we see them. So LIGO is now in the 120 plus baryon-neutron star range. Virgo is also acquiring data at actually a little bit lower. It's order of 50 megaparsec range for baryon-neutron stars. And we're hoping that CAGRA will join soon for the second part of our run. There is a plan to have an 04 run where advanced LIGO will reach its maximum possible sensitivity. And then the plan is to upgrade to the so-called A+. So here we're talking about 2025, 2026, and I will say a little bit more about it then. We are in an era of open data, so the data is being released after proprietary periods. So all the data from O1 and O2 is now public. O3 will become public within a year and a half of each 6 months cadence. And this is giving us this is a plot of the range. So how far can we see BNS events during the first parts of O3. So this is this first period between April 1st and October 1st. We had then a break of a month for commissioning. These dots, let's see, so this is the Livingston range, Hanford range, and the Virgo range. So Virgo has been stably around 50. Livingston order of 130 megaparsec, and Hanford about 100. And these are the duty cycles. So we have three, for about half the time, 44.5% of the time, we have three detectors operating. So that's what determines our effective data acquisition time. I was mentioning that we are distributing data, but not only that, we're also propagating now alerts every time there is an event of interest that's showing in our online analysis. So, so what you see here is on a calendar, each day that we've had in alerts being produced by the LIGO Virgo data acquisition system. So whenever we have a candidate that's of interest, and we can determine whether it's more likely to be a black hole binary or a binary neutron star binary or possibly a neutron star black hole binary, an alert is sent out. The ones that are circled in red are more likely BNS events. The green is for neutron star black hole binary events. And so you see that we've had quite a few that are now being distributed, and we're now working on analyzing that. But this is giving you a sense of how many candidate events are now available. This is a website where anybody can actually get a map, access to a map for the localization. So in some cases, there is a terrible localization. In other cases, you have something that's more likely to be followed up. To date, we have 25 binary black hole candidates, 3 binary neutron stars, 2 events that could be in the mass gap, so between 3 and 5 solar masses. That's the gap between what we expect to be neutron star and black hole, so this kind of weird area. We have 4 potential NSBHs, but 3 are very high false alarm probabilities, so they could be due to just chance coincidence between glitches. And this is not too dissimilar to the rate estimates that we can do so far. So for binary neutron star, the expectation is that we can have up to 1 event per month of data taken. The median is 2 per year of data taken. So there is a large fluctuation. But if we look here, you know, we have 1, 2 possible binary neutron stars. There are a lower false alarm rate, and then there are a couple with low false alarm rate, and there are a couple with high false alarm rate as well. For binary neutron star, the expectation is between 1 a month to 1 a week, and I would say that that's consistent with the data that we've been receiving so far. And SBHs are, the range is too uncertain to say, and we don't know what to expect for other sources. But O3 is already promising to be rich of events, and at the very least, we're going to have lots of binary black holes to add to our catalogs. So now let's talk about the future, what's going to be coming next. So in the near term, so that the O4 run will be the run in which advanced LIGO will be at its maximal sensitivity. So here we see where the noise sensitivity was in the O2 run, and this is the expectation for a LIGO at full sensitivity. So what do we expect to have by then? So I'm just going to kind of walk a little bit here through the expected rates for the science that we're expecting to do at that point. So the reach is supposed to be about twice what it was in O2. Order of 100 binary black holes per year, so up to a Z of close to 2. 1 to 2 neutron star black hole per year, and between 20 and 30 binary neutron stars per year. With all these binary neutron stars and binary black hole, we can also start to narrow down a little bit the estimates of things like the Hubble constant. So we could potentially get to order of a 4% H0 determination. And then when we start thinking about the ringdowns, the quasi-normal mode for the ringdown for events such as the GW150914, well, in the full sensitivity advanced LIGO, that event would have had a signal-to-noise ratio of 20. So tests of GR may become possible to a higher accuracy. So far, we have not been able to find any deviation from GR with the sensitivity we have. In the medium term or in the future, A+ is a planned upgrade where there are modest upgrades to the advanced LIGO and Virgo as well, such as the introduction of frequency-dependent squeezing and possibly a lower thermal noise optical coating, so addressing two of the main limiting sources of noise for advanced LIGO. So that should give us another improvement in sensitivity. So we're now talking about 3 times, so 2. A rate of BBHs of order of 500 to 1,000 BBHs per year. 10 neutron star black hole mergers per year. 2 to 300 BNS per year, and even higher SNR for the ringdowns. So order of 1,000 binary coalescences per year. So then what's next? So then we start talking about third generation technology. So to go to better sensitivity, we need much more aggressive technology upgrades. So one of the concepts that are currently under study actually here, so I don't want to say too much because if I say wrong, Ran is going to come after me later. So this is a concept of basically changing from the existing mirrors to something that's much bigger. So moving to silicon optics, much heavier, so more than 100 kilograms now, with new coating and operated at mildly cryogenic temperatures, so 123 Kelvin. The new mirrors are going to require new type of lasers, so going up to a 2-micron, 300-watt laser. And this type of technology installed in the current detector, so in our 4-kilometer baseline detector, would increase the reach substantially. So taking the BNS reach up by a factor of 10 compared to 2. BBH is detected up to Z of 5, and a very high signal-to-noise ratio for the quasi-normal mode ringdown. So that's one of the possibility. I would call this 2.5 generation because it's third-generation technology in second-generation detectors. What is really the third-generation outlook now is a much bigger detector. So to increase and do a real jump, we need to go from the kilometer scale to the tens of kilometer scale. So the two designs are the Einstein telescope and the Cosmic Explorer. So Einstein telescope is based it's a European conceptual design study. The idea is to have multiple instruments in a xylophone configuration. It's underground. The arm lengths are 10 kilometers, and it's in a triangular shape. So this is going to require another 10 to 15-year technology development, but the planning is proceeding rapidly. Cosmic Explorer is an NSF-funded U.S. conceptual study where basically the idea is to just keep an L-shaped detector, but much longer. So the signal amplitude will grow with the length, but not most of the noise sources, so those get diluted. And so that will give the added increase in sensitivity. And so just to give a sense of the potential, I'm just going to put up this graph that's showing basically what was the O2 sensitivity, what's the target advanced LIGO sensitivity, so that's our target O4 sensitivity. LIGO A+. And then here are 2 stages for the Cosmic Explorer. Einstein telescope will be probably around this range too, but going to lower frequency. So there are some differences in the spectrum. But this kind of gives you a sense of the sequence for the sensitivity plan for the future. And now what we see here is the range. So in these plots, away from the center, that's the range. So this is a Z of redshift 0.1, redshift 1, redshift 10, redshift 100. And this is basically where we expect the reaches to be for neutron-star binary or black hole binary. And so in the 3rd generation of detector, the aim is to be all the way out here, which is at high Z, above Z of 10. And the neutron-star binaries will be visible in detectable in most of the visible universe. Now, it's not only important to have sensitive detectors. We need multiple detectors to be able to localize the position of the source position itself and enable more of these multi-messenger follow-ups that we had for GW150914. And so, so that's why our upcoming networks in the 2G network is going to include Hanford, LIGO, Virgo, Kagra, and India. I think as I was talking about the network, I forgot to mention India. So this is a plan to bring an A+ type detector in the A+ timeline, so 2025 roughly. A detector similar to A+, so same configuration, but located in India. And so that will add another component to the multi-network that will give the ability to disentangle polarization and localize the sources. And so, so what we have up here is basically the prediction going from the 3 detector to the 5 detector with Kagra in India, and then an advanced detector, a 3G detector network with, in this case, is 1 Einstein telescope and 2 Cosmic Explorer, just to just as an example of possible events. And so the total number of events detected goes from order of 50 per year to 990,000. This is the number of events reconstructed with error region of 1 square degree, 10 square degrees, 100 square degrees. And so you see there are a very large number of events that will be very highly localized. And so that will open all sorts of potential for doing things like understanding source population for black holes and neutron stars. So starting to answer questions such as, are these black holes primordial? Are these black holes forms from stars? How did they get and come together? What can we learn from these black holes about cosmology? Can we go after stochastic backgrounds? So it's, and then from the neutron stars, can we really pin down the equation of states? So these are all areas of future investigation that are going to be open and lots of new excitement. So, so I'm going to end here. So just 5 minutes to the end of the hour, so that we can do some questions. We just this image that it's an artistic rendition of the GW150914 events, and it's multi-messenger nature, and just leave it with the notes that this is really the beginning, and those of you who are graduate students now really have an opportunity to explore new paths. So, so welcome to the new era of multi-messenger astronomy. Thank you. Yeah, so let me pull out. I think this is, yeah, I've not talked so much about the stochastic backgrounds, but maybe it's easier if I put up this kind of landscape plots. So LIGO is sensitive to the kilohertz range. So this is a plot of omega GW versus frequency. And so our regional sensitivity is all up here. So far we have not identified stochastic events from O1 and O2, so stochastic gravitational wave backgrounds. And our limits is still above any of the other indirect limits that could be put. Now the hope is that with advanced LIGO at full sensitivity, we can start tapping into some of the models, stochastic backgrounds, that are connected to astrophysical background, for instance. So at that point, we should start being able, some of that popcorn noise that's coming from old binary black hole mergers or very far away binary black hole mergers. So there is some potential that in this is the gray area of astrophysical background here that can be tapped. 3G will have several order of magnitude improvements on the omega sensitivity. Now, limited from the CMB, those are a much lower frequency. This is, inflation model are all the way down here. So equation of state limits, this is what Lisa's going to be doing. So we have a limited window on the stochastic background, but at the very least, we should start to be able to tap into the astrophysical one soon. The cosmological is going to be tough, but we'll see. Definitely not in the second generation. I was being kind.
Would you like to tell us more about GW150914, the first high significance neutron star black hole merger?
Oh, we're still working on that. I don't know that I actually know what to tell you about it. Yes.
We can tell you afterwards, but we're being recorded right now.
Mm-hmm.
Where would those be on this sort of diagram, and how close are you technically?
Yeah, I wouldn't look at them on this diagram here because this is omega GW. So for bursts, well, bursts is kind of hard to place them. So we can maybe think about source by source. And the core collapse supernovae are the one, when somebody was asking me earlier, what do you think is going to be I think you were asking me earlier, right? What's going to be the first burst signature? And core collapse supernova is the one I understand better, so I would probably go there. Now, the problem with the core collapse supernova is that we don't know how much gravitational wave is going to be produced. Now, most models are predicting that it's going to be a very small amount, 10 to the minus 2 solar masses emitted in gravitational wave. And so for that small amount of gravitational wave, they need to be closer, so they need to be galactic. So even reaching out to Andromeda in this kind of more standard model is going to be tough. Now, there are more extreme models that are predicting, it all depends on the physics that's in there. So we are actually running searches for core collapse supernova type waveforms. We do look for them. We haven't found any coincidence. You're expecting to see it electromagnetically as well. We're also working with neutrinos because now there could be a core collapse supernova in a place that's blind. We cannot see it electromagnetically, but they will be seen by neutrino experiments. So we're kind of casting a broad net, and that is being looked for, that kind of coincidence. But again, we have not seen that yet. If there is a core collapse supernova in the galaxy, everybody's nightmare is that it's going to be during a commissioning period. So that's why GW600 is running in AstroWatch mode during commissioning. So at least we have one detector running.
Are there current limits on the particle movements of neutron stars?
Yes, but I don't have them handy. Yes. That's we have these continuous wave searches. We're different type. There are searches that go after known pulsars, and so you target those specifically. And we also have all sky searches that are basically looking, at in all frequency bands for signal that are periodic and they are they're consistent with the gravitational wave signal. Now, those have only provided upper limit searches, and they have produced the limits on the ellipticity of the neutron star. I don't have those numbers handy though right now, but I can point you to the right direction.
Well, we have moved our refreshments to after the talk, so we can always, if we have more questions, you can join us in the east-west bridge